All right, as we continue, we're going to talk now about graphing sinusoids, which sinusoids are both sine curves and cosine curves. More in that rectangular region that we're used to doing on the rectangular coordinate plane. If you think about what we did in the last section in 4.3, we were doing things more circular. So if I took the sine of 30 degrees, it was going to be the same as the sine of 390 degrees because they were coterminal. But when we look at things where, say, my angle and my value of y are changing as I go from left to right, I could think of something like y equals the sine of theta, again on this rectangular coordinate system. If I take the sine of 0, I get 0. As I take the sine of 30, I get 1/2. If I take the sine of 60, I get the square root of 3 over 2. The sine of 90 is equal to 1. Then as I continue into the second quadrant, the sine of 120 would bring me back to square root of 3 over 2. The sine of 150 would bring me back to 1/2. And the sine of 180 is actually equal to 0. When I head into the third quadrant, sine becomes negative. Sine of 210 is negative 1/2. The sine of 240 is negative square root of 3 over 2. And it continues on with a form that's going to look like this. So if I went to negative 30 degrees, it's negative 1/2. If I did negative 60 degrees, it would be negative square root of 3 over 2. And so we have this function that looks very much like this and continues on and on, doing the same up and down motion. I told you that cosine is also considered a sinusoid. When I think of sine, I usually will use the word it starts at 0. Well, it doesn't start, but using the terminology we've had before with initial value, the initial value of sine at 0 is 0, and it goes up and down. It keeps going up and down. When I think about the initial value of cosine, the cosine of 0 is actually equal to 1. And then it goes from there to square root of 3 over 2 to 1/2 to 0. It's not showing as much of a curve as I'd like. And then it goes down. The cosine of 120 degrees is actually going to be negative 1/2. And then negative square root of 3 over 2. And then the cosine of 180 is negative 1. So it's going to have kind of the similar shape, and it'll start going up again. It'll end up overlapping at places. It'll overlap here at 45 degrees, and they cross again at, let's see, 180 plus 45 or 225 degrees. I don't have that perfectly lined up. But cosine ends up having that same almost wave-like look to it. Let's see. If I went to negative 30, that would have been at square root of 3 over 2. And this would have been at 1/2. So it should have been more like that. So we get the idea that both of these are what we consider sinusoids because they have this flow. You can actually put this in your calculator and watch how your calculator graphs it. Ask me in class and I'll try to help you set that up if you'd like to see it. But in general, both sine and cosine are called sinusoids. And so going back to our previous chapters, we can look at sinusoids basically as transformations to the basic functions that we have here. So this is sine and cosine, and we can look at things. So I'm going to erase this and give you the basic function for sinusoid. It would say f of x equals a times the sine of bx plus c plus d. Now that's taking our basic sine function and making some transformations. If you guys remember from the things that we've done in the past, if we had a function, say g of x, that was equal to x plus 1 squared times 3 minus 5. The transformations that we would say here is we'd go 1 to the left, we'd do a vertical stretch of 3 and move 5 down. Okay? I'm going to do the same thing with sine curves. If I have something being multiplied out in front, I'm going to have a vertical stretch. I'm doing these in order that we see them, not in the order that they would occur. Vertical stretch of A. I would move C to the left. I would go D up. And B would be, I didn't have an example that was analogous in this one. B would be horizontal shrink if it was greater than 1 in this case. So, of course, if any of these things are negative, they're getting flips and all that other stuff that we did in earlier chapters. But they use different terminology in sinusoids. Okay? So, if we just look at the sinusoid, normally a sine curve goes something like that. It goes as high as 1, as low as -1. Okay? We would say that the amplitude is 1 because basically it's the total height of the wave minus the depth of the wave divided by 2, or something along those lines. Our amplitude, when we do transformations, changes to A. So if I had just a function that said g of x equals 5 times the sine of x, the only thing that would change in that graph is instead of just going to 1, it would go up to 5 and down to -5. So it would just look like this. So we would have a vertical stretch going on, but the key word here is amplitude. Often we'll ask in a sinusoid, what is the amplitude? Okay. We also will talk about the period of a sinusoid. And if you notice in all my drawings so far, I can basically just go, it has the same shape again and again and again. The period is how often does it take to repeat. So one full period of a sinusoid is basically represented by that. Okay. Here's the second period. How long does it take to get through one full period? Well, the default period for sine and cosine is 2 pi radians, or 360 degrees. Okay? And what's going to affect that? No translations are going to affect that. A vertical stretch doesn't affect that. Flips don't affect that. The only thing that would affect that is this value of b. Okay? I'm either doing some sort of a horizontal stretch or horizontal shrink, and that would change the period. So the period, when I have a value for b, is equal to 2 pi over b, or 360 over b. So again, to give you an example, if I said g of x equals the sine of 2x, what that's going to do is, instead of me taking 360 degrees to go through one full period, this would cause a horizontal shrink, and it would shrink everything in half, or I could actually get a full period in 180 degrees. So that's the idea of period. Now, there's a term that your book uses. We don't do it a whole lot, but frequency is basically the inverse or the reciprocal of period. So it's b over 2 pi or b over 360. If you see that in other places, it's very common, and it's related to period, but it's not exactly the same thing. All right, last thing I want to talk about as far as just the vocabulary. We talked about period, we talked about amplitude. We also get this term phase shift. And phase shift is analogous to our horizontal translations. And it's a little bit tricky because of how this looks. If B was the period, C is not the only thing that's occurring here. It's not like the phase shift is just equal to C. Wouldn't that be nice? Because I could look at this as A times the sine of B, X plus C over B, right? If I factored out that B. That ends up giving us our phase shift. That's a terrible B. Our phase shift ends up being C over B, okay? If it's negative, it's moving to the right. If it's positive, it's moving to the left. So really, I should just call it C over B. Again, phase shift refers to a horizontal translation. And we'll look at some examples of that in just a moment. So some of the things you'll have to be able to do is just like we did before, identify what a graph would look like, identify the parts. If I give you the equation, what's the amplitude, what's the period, what's the phase shift, and if I tell you those things, come up with the equation. So very similar to how we did transformations with functions before.